Alright, let's look at the case of finding our e to the jt or j to the k power when our Jordan form is not just a diagonal matrix. So finding these for non-distinct eigenvalues. Okay, remember when if we have our Jordan form j for distinct eigenvalues, let's just review a little bit first, I guess. Distinct eigenvalues, we would have something like this for a Jordan form: lambda 1, lambda 2, lambda 3, and zeros everywhere off the diagonal. So that gave us e to the jt was e to the lambda 1t, e to the lambda 2t, e to the lambda 3t, and zeros everywhere else. And similarly, our j to the k just became lambda 1 to the k, lambda 2 to the k, lambda 3 to the k, and zeros everywhere else because of the nice diagonalness of the J matrix. And remember, we could just find these. This isn't a magical formula. We can find either the JT just like we do e to the AT by a couple methods, but maybe the favorite is Laplace inverse of SI minus J inverse then. So we typically put A in here, but we can put J in here as well. And so that's what we'll do now for the case of a Jordan form that's not diagonal, but if you want practice, you can put it in there. Similarly for J to the K, so this was e to the JT. Finding J to the K, just do Z inverse of ZI minus J inverse times Z, like we would for any A to the K matrix. Alright, so let's do this for the case of a repeated eigenvalue. We'll just do one simple case here. Let's try a J like this. Lambda 1 is distinct, but lambda 2 is repeated, and we have a Jordan form that looks like this. Okay, so for each different Jordan form, you'll have a different e to the jt. Alright, so let's find Si minus J. Let's find e to the jt first. Okay. Si minus J is going to be S minus lambda 1, S minus lambda 2, S minus lambda 2, zeros, but then here's going to be a negative 1. Okay, so it's not a purely diagonal matrix anymore. And then we want to, eventually we're going to have to find the inverse of this, so let's find the determinant of it first. Determinant of Si minus J is going to be, let's pivot around the 1, 1 term, so we're going to have S minus lambda 1, and then our determinant of the inner one is just S minus lambda 2, S minus lambda 2, minus 0. So S minus lambda 2 squared gives us our determinant. And then we need our cofactor matrix. Alright, to find our cofactor matrix, let's start building it, I guess. We'll put our plus and minus signs for our adjoint and put our empty spaces for our determinants. Our 2 by 2s we're going to have to fill in here. And don't forget the transpose. Alright, so looking at our 1, 1, our first row, first determinant is going to be S minus lambda 2, negative 1, 0, S minus lambda 2. Second one, 0, 0, negative 1, S minus lambda 2. We're going to have lots of nice zeros. 0, 0, 0, S minus lambda 2. Second row, first column, 0, 0, 0, S minus lambda 2. S minus lambda 1, 0, 0, S minus lambda 2. S minus lambda 1, 0, 0, 0. And then a third row, S minus lambda 1, 0, 0, S minus lambda 2. Oops, 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 oops. Gotta move my pencil. 0, 0, s minus lambda 2, negative 1. Since it's got 2 zeros on the top, this one's going to be 0, so we won't worry about making it too neat there. This one, s minus lambda 1, 0, 0, negative 1, s minus lambda 1, 0, 0, s minus lambda 2. First one, s minus lambda 1 times, s minus lambda 2 times s minus lambda 2, so we're going to get s minus lambda 2 squared minus 0. 0 minus 0. Over here is also 0 minus 0. Get those taken care of. The center term is going to be s minus lambda 1 times s minus lambda 2 minus 0. So s minus lambda 1, s minus lambda 2. Third row, second column, s minus lambda 1 times negative 1 minus 0. And then another minus, so it's just going to be s minus lambda 1. And then our last term here, s minus lambda 1, s minus lambda 2, and 0. Si minus j inverse is then 1 over our determinant, s minus lambda 1, s minus lambda 2 squared, times our matrix. Now, taking the transpose, we have s minus lambda 2 squared, s minus lambda 1, s minus lambda 2, same thing. But now we have our s minus lambda 1 over here. If we go ahead and divide through, and then our off-diagonal term, s minus lambda 1 here, cancels, and we end up with a 1 over s minus lambda 2 squared. Alright, so to finish finding our e to the jt, we need to take the Laplace inverse of our matrix we just found. Do that term by term. 1 over e to the s minus lambda 1t just transforms to e to the lambda 1t. Same thing for the other two, e to the lambda 2t, e to the lambda 2t. And so if you were doing a Jordan form with distinct eigenvalues, all you had were the diagonal terms. This is what you would have. But now we have one more term because of our 1 in our Jordan form. If you had a different kind of Jordan form, you might have more than one off diagonal. So we also need to transform this one, transform a pair for 1 over s minus lambda 2 squared. We're going to get a factor of t e to the lambda 2t. So we have our e to the jt found now for our non-distinct eigenvalue case. The main difference is this one off diagonal term.